Okay, welcome to lecture 4 of data mining at Google. Today I want to finish up a little bit of chapter 2 that I didn't get to last time, and then I want to get into chapter 3, which is sort of one of my favorite chapters because we get into visualization of data, so we start making plots and things like that. And R is very good for making plots. That doesn't pertain to you. Okay, so this homework assignment, it's due for the students that are taking it at Stanford on Tuesday. So remind me after that I can email around the solutions, or I'll probably have them up on the web page. So if you want to try doing some of those exercises, then you can check your answers with that. Chapter 2 we were into last time, and we talked about data in chapter 2. Basically, we tend to perceive data in this matrix form where the rows are what your book calls objects, I call observations, and the columns are different attributes, or what I would call variables. And the last thing we were talking about was, suppose you get a data set that's big in the sense that it has a lot of rows or a lot of objects or a lot of observations, and maybe you're trying to compute something like you just want to know the mean or average taxable income, right? You just want to know what the average is in your data set. Well, it may be sort of inefficient to sort of do the mean of the entire data set. If you could just take a random sample, that may be sufficient. So last time we were talking about sampling, which is using only a random subset of the data. Statisticians often do sampling because they can't get all the data they want. They can't get all the data from a large population, for example. They want to know the percent of all people that will vote for a candidate. Well, they can't ask everyone in the US who's going to vote for a candidate, but they can take a sample. Data miners like to do sampling because often they have all the data, or as much data as they really want, but it's sort of just too slow or too cumbersome or unnecessary to work with the whole data set. So we often just take a sample if that's going to give us an answer that's close enough to what we're after. And I think I mentioned to you this time that I got this quote from the book, but it's very circular, right? It says basically a sample will work almost as well as the entire data if the sample is representative. What does it mean to be representative? Well, that means it has the same characteristics. So it's quite circular, but the point is it really depends on what you're after. If you're after just the average, well, then the sample might be good enough. If you're after sort of the largest case, well, your sample is probably not going to contain the largest value, so the sample's not going to work good enough. So whether or not the sample works well or not really depends on what you're after. But for many things, if you're just after like the mean or the median or the first quartile or something like that, you know, doing it on a very small sample might give you the same level of accuracy as you would get on the whole data set to the point where you actually care about it. So often sampling can be very effective. Simple random sample is the most basic type. Basically, you think of it as drawing numbers out of a hat or drawing names out of a hat where each name or each number corresponds to a row in your data set. So you think, put all the rows of your data set into a hat and draw them out. It can be with replacement or without replacement. Someone asked about the distinction between that last time. Usually it's not a big deal as long as the sample size is small relative to the whole data set. Generally, you like to do things without replacement, but as we discussed, sometimes it doesn't really make sense. So you do things with replacement. And then there's more complex schemes. And I think last time I showed you in Excel how to draw a simple random sample. Basically, all you need is a pseudo-random number generator and you're in business. And there's one of those in Excel, which is the rand function. You can use that. By default, it draws numbers uniformly between 0 and 1. And then you could sort on that, and that would give you a random sample without replacement. And if you wanted to do it with replacement, you can imagine how you would do that. And here I have some screenshots, I think, of what we went through last time. Basically, this last column here was a random number I generated using the rand, and then I simply sorted on that, and then you can pull off the top rows. Now in R, there's this function called sample, which works pretty well. One of the advantages to using this function sample is anytime in R you can use some of their built-in functions and avoid doing a loop, it'll make things much faster because loops in R are really slow. So this sample function is nice. It prevents you from having to sort of do a loop and calling the random number generator each time. And so the arguments it takes, you see here, x, which is what you want to sample, the size, then the default is to use without replacement. So sometimes you have to override that to true if you want to do it with replacement. And I think last time we left off here, I was drawing a sample of 10 observations from our Stats 202 log data set. So let's see, how do we do that? Well, I put the code up here and I'll sort of tell you what this does. Basically, I'm creating a new object called SAM, and that's going to be a sample. So sequence of 1, 19, 22. I'm going to get a sample of 10 integers from the sequence of integers 1 to 1922, and I'm going to do it with replacement because I asked you to do it with replacement. So that's sort of the first step, and I think we probably did that. So if I just say take this command, now notice I called it SAM and not sample, because if I called it sample, of course, I would be overwriting the sample function and it wouldn't work. And R does let you overwrite things like that, and you can get yourself into trouble. So now SAM is basically 10 integers between 1 and 1922, sampled randomly with replacement. Okay, now how am I going to use that? Well, I'm going to use that to index into my data set. In particular, I'm going to take out these rows, and that's going to be my random sample. Now, I need to read in the data, so let me find it. I think I should have a local copy of it sitting around here somewhere. This is what, stats 202 log. Let me just put it here where I remember where it is. Let's see, grab the path, and I'll set the desktop to be my working directory. So throughout the day, anything I save or anything I load will be set working directory desktop. What? Oh, I spelled working directory wrong. WD, working directory. And I usually include a command like this in the beginning of my script. However, if I move my script to a different folder, then I often have to update that. Okay, and I'm going to do read, let's see, let's call this data read.csv. Let's see, it's called stats 202 log.txt. And it's crucial to say that the separator is a space and the header is not there. Oops, that's an equals. Okay, and there's a cute little feature here. If you want to sort of see it in a spreadsheet, there's something called data editor under the edit menu. And I can type in to see what this looks like. Whoops, what just happened there? I called it dat. Well, it's going to be called, let me call it data. That'll confuse me. Data. Okay. So say edit, data editor, data. There we go. So you see here, this is sort of a preview of what the data looks like. And you know, it sort of chops things off depending on the size of the screen and things like that. And the other command that sort of is nice sometimes, head of data, I think just gives you the first 5 rows by default. So anyway, I've read in the data. I have my SAM object, which is the numbers of the rows that I'm going to take in my sample. And then I simply say here, so the question said, okay, I should say here. The question said, draw a sample from the first quantitative attribute. Now, if you remember that data set, it turns out the 7th column is the first one that R thinks is quantitative. It's not really quantitative because you know, so data $V7 will give you the 7th column. Oops, V7 will give you the 7th column because the names of the columns are like V1, V2, V10, et cetera. So $V7 will give me the column that's called V7. That's equivalent to saying data nothing, comma 7, the 7th column. And you see, R thinks this is numeric, right? It's not a factor. It thinks it's numeric. 200, 404, I mean, we know that this is not numeric. We know that these are codes and should be treated as categorical. But R thinks it's numeric, and I want to play with a numeric example. So let me just pretend this thing is numeric. Okay, even though it's not really, I guess I'm illustrating, you know, one of the things I tell you not to do. Don't treat something as numeric if it's not. But just for a numeric example, I'm going to use this one. So what am I going to do? I'm going to take the rows that are numbered SAM. So I'm going to say data $V7, which is that whole thing of 1922, and just the rows that correspond to the numbers SAM. And that's going to be my random sample. So what did I call that on the slide? I think I called it my sample. So say my sample store as this thing, data $V7, which is the 7th column, and just those rows. What? Oh, that's going to be a disaster. Yeah, okay, there we go. My sample. There we go. So it's just those rows. Okay, so I think that catches us up to where we were here on the slide. So I have an object called my sample that is a sample of 10 objects from that data set. Now the question is 10 good enough, right? And of course it depends, well, what are you trying to do? Well, suppose I was trying to figure out the mean of the 7th column. How well can I figure out the mean of the 7th column with just 10 numbers? And that's sort of what this slide is asking. It says, if I do the sampling in the previous exercise repeatedly, roughly how far is the mean of the sample from the mean of the whole column on average? So we can sort of see for one instantiation here. See if I can blow this up a little bit, make it a little bit bigger for you guys. Let's see, GUI preferences. Let's do a font of size 14. That should help a little bit. If I go down here, there you go. Okay, so if I take the mean of my sample, I can't type today. Okay, it's 261.2. So let me So this is sort of the mean of my sample. So it's called a sample mean. And this time came out to be, what, 261.2. And then we could compare that to the true mean. Now, in general, if you didn't really want to mess with the whole data set, you wouldn't really know the true mean. But here, it's only 1922. So let's just look at the mean of data $V7. And so the real mean is 299.3. Let's just call it like, roughly 300, right? OK, so our delta, or we call it like our absolute delta, sort of the price we paid for taking just 10 observations as opposed to all 1922, we're off by roughly 40. OK, so that's sort of the price we paid. And you can see if you do this thing repeatedly, if I take another sample, let me go back and just do this a couple more times, take another sample and get that guy, and then again, take my sample to be that, figure out the mean of my sample. This time I got 342.8, right? It depends on what 10 observations you get. So then I got 342.8. The true mean, is still roughly 300. That doesn't change. So now I'm off by, I guess I'm off by about 40 in the other direction. Sort of cute. And let me do it one more time just so you sort of, again, take a sample and figure out the mean of it. And this time I got 302. So I'm really close this time, right? So the true mean is approximately 300. So this time my delta is about 2. So off by 40, off by 40, off by 2. OK, so the question is, on average, how far are we going to be off? If I keep doing this over and over again, what's like the average value of these deltas? And what you can see up here is I wrote a little loop to do that for you. And this is sort of the first loop we've put up in R. So I'll sort of mention what's going on here. First thing, because I don't want to call mean every time in the loop, I just take a constant and store that as the mean. So real mean, store as the mean of the 7th column. So this real mean object is basically going to be, about 300, whatever that 299 point whatever was. Now, I like to initialize variables in R, which you don't really need to do, but I get in the habit of this. So I'm going to store the differences in this vector, and I'm going to go through this loop 10,000 times. So I just create a vector of all zeros and a vector of like 10,000 that's all zeros. And I'm going to put the differences in there. So like, these could be the first three, 40, 42. I'm going to do it 10,000 times. And then here I start writing the loop. And so this is sort of how a loop looks in R. For k in 1 colon 10,000, right? So k is going to start at 1 and go up to 10,000. Each time I'm going to draw a sample. So this command is the exact same thing I did before, sample of size 10 with replacement. Then I'm going to say my sample. I overwrite my sample with data $V7, whatever the rows are from this sample. And then store difference. The kth element of store difference I'm going to put as the absolute value of the difference between the mean of my sample and the real mean. And then I'm going to compute the mean of those, which this time I did it came out to be about 25.7, or what I said here, about 26. Here you see, I got 40, 42. The claim is that this thing averages, roughly 26. And, just for sake of doing it in real time, you can see what would happen if I would do it here. So let's see, the real mean, that's going to be this 299 point whatever number, right? Real mean. And then the store difference I just initialized, that's just a vector of all zeros.
Can you do it 100,000 times?
Yeah, let's do that. Why not? 100,000 times. OK, one more zero, right? OK. And then I have to change this one to 100,000. The loops in R are really slow. Oops, shoot. Do that one. OK, 100,000. OK. What's the what stand for? Where do you see RAP? Oh, rep. OK, a rep, it just means like repeat that thing that many times. So if you did question mark rep, you would see the first argument is what you want to repeat, and the other thing is how many times you want to repeat it. So that's just going to be a vector of 0 repeated 100,000 times. Let's see. It's just my way of initializing it and initializing it at 0. I don't know, maybe it's a bad habit, but it's sort of a habit I got into at some point. OK, so I'm still going to take samples of size 10. And then let's see, each time we're going to make my sample to be those 10 guys. And then I'm going to compute the difference to be the absolute value of difference between the sample mean and the real mean, and then close that. So it goes 100,000 times. You keep wait. The loops in R are you know, slow, right? Oh well, that's life. And then let's see, the mean, probably pretty close to 25 point something, 25.5. So we call it about 26. So we're off by an average about 26. So 26 is sort of the price we pay for taking just 10 observations as opposed to taking the whole 1922. And so you say, well, if 26 is too big of a price to pay, if you don't want to be off by 26 on average, what do? Well, then you take more than 10. The interesting question is to see how sort of our error scales as we increase that. But before I get onto that, anyone have any questions about sort of this R commands on the slide here? Okay, so it's your first example of writing a loop in R. Don't get into too much of a habit of writing loops in R because you see that they are pretty slow. But, you know, for simple simulations, you can just say, well, I don't want to think about it. I'll just write a loop and see how it goes. Okay, so then the question is, you know, if I'm off by 26 on average by taking a sample of size 10, what if I take a sample of size 100, right? Then I should be closer. And here you see I wrote the same thing, except I changed the sample size to 100, and now I'm only off by like 8 on average, right? So I went from having an error, we call this sampling error of about 26, to a sampling error of about 8, meaning the price I'm paying for taking 100 as opposed to all 1922 is I'm off by about 8. And so the question of how big the sample is depends sort of on, well, how close do you really need to be? Now, the interesting thing is that you'll see that it actually scales as a function of the sample size more so than a function of the whole population size. So, you know, you say 10 or 100 or 10,000, you know, and you're going to get closer and closer and closer no matter how large the data set is, which is sort of interesting. But the point here is that by going from 10 to 100, now we're only off by 8. If you want to be closer than that, you could go by 1,000. But the thing to talk about now, let's see, where's this eraser, is that I want to just mention the relationship between the sampling error, which here we saw went from 26 to 8 as I increased the sample size from 10 to 100. And that actually illustrates sort of the point I'm going to make. If we have a sample size of 10, so let me call this sample size. Sample size of 10, we saw that our average delta, which is what I'm calling my sampling error, was about 26, roughly. And when I used a sample size of 100, my average delta was about like 8.1. Okay, so the question is, you know, this thing is decreasing as this thing increases, but the question is at what rate? Anyone know what rate? Square root, right? Turns out to be the square root. And that's sort of what I said here on the next slide. It's the square root sampling, what did I say? The square root sampling relationship. When you take samples, the difference between the sample values and the values in the entire data set scale is the square root of the sample size for many statistics, such as the mean. It's not true for everything, but it's true for the mean, true for the median, true for any percentiles, true for a lot of things. Wouldn't be true for the max, for example. Okay, for example, in the previous exercise, we decreased our sampling error by a factor of the square root of 10, right? By increasing the sample size from 10 to 100, since 100 over 10 is 10, right? So I went from 10 to 100, which means I increased my sample size by a factor of 10, which means I should have decreased this by a factor of the square root of 10, which is about 3.1, right? Oops, where are we at here? Square root of 10 is about 3.1, so roughly 3.1. And likewise, the ratio of 26 to 8.1 is about, should be 3.1, right? 26 to 8.1. Oops. 26 to 8.1, about 3.2. So, you know, actually, this one is also 3.2. So perfect, right? Perfect if you only keep one decimal. So that's the square root relationship. The interesting thing to note is that it's only the sizes of the samples that matter and not the size of the whole data set, because this relationship basically is assuming an infinitely large population. So of course, this relationship sort of doesn't work as well as you start to have a sample size that's closer to the whole population size, but usually the sample is small relative to the entire size of the data set, so this relationship tends to work pretty well, and so you can imagine that your sampling error generally scales as the square root of your sample size. Why is this true? Well, it's a pretty trivial statistical exercise to see that the variance scales linearly when things are independent, and then the standard deviation being the square root of that scales as the square root of the sample size. Question?
So are you assuming like the population is uniformly distributed?
So the thing you need is that the sampling is independent and that the observations are independent. That's what you need. That's what you need. Yeah, you need it to be, you need things to be independent. So that's why you can add the variances, right? You can add variances if things are independent, and so you add the variances of n thing, it goes like linearly, and then the sample is divided by n, so that's divided by n squared, so then you get the 1 on n and the square root 1 on n. Okay, so this is sort of a basic result from statistics, right? Because statistics does a lot with sampling, not because they get huge data sets, but because they get small data sets and they want to know sort of what their sampling error is. Okay, any questions on this square root relationship? Question in the back.
Would it be improper to call it an inverse square root relationship?
Yeah, probably that's better, right? So we know that the sampling error goes down as the sample size goes up. So really an inverse square root relationship, right? Right. And in particular, the sample mean, if you're curious, actually scales as the standard deviation divided by the square root of n. But other statistics will scale with other constants, but the square root of n is always going to be in there for most of these things. Other questions about the square root sampling relationship or the inverse square root sampling relationship? Okay, so that's actually all I wanted to say about chapter 2. Oh no, not all I wanted to say about chapter 2. One thing about sampling is that it's not the answer to everything. If you have these independent observations, right, if you can imagine your data looking like independent rows, and it doesn't really matter which rows you get because all you're going to do is something like the mean or something like that, then sampling, sure, that's easy. But when you don't have this independent structure, like, so for example, here's words of a song, right? Words of a song are not independent. If I just take a random sample of words from a song, I have no idea what the song is about. Other applications, right? If I take independent samples from my weblog, well, that's not really the right thing to do because I get, this person doing this thing and this person doing this thing, but I don't really know what any one person did. So instead of taking independent samples from my weblog, maybe I want to sample IP addresses, or even better, if I knew who the users were, I could sample users, or maybe I want to sample days, right? Out of 365 days, I want to take 10 days. Internet searches, right? You don't just want to sample from your logs certain actions, right? You want to sample a click from this person, a click from this person. You'd rather sample the entire session from a small number of people, right? Or at least the entire query session from a small number of people. So you really need to think about not breaking relationships. And in this sort of toy example of a song, instead of just sort of sampling words, you might want to sample complete lines, right? So not 10% of the words, but 10% of the lines. Or maybe you want to sample, if you have a whole bunch of songs, not 10% of the words, but 10% of the songs. You need to sort of keep units intact when there's dependencies within the units. Now, the tricky thing is, with a large data set that you haven't explored that yet, you might not really know what these dependencies are that you need to keep intact. So sampling as sort of a first thing to do is not always the best thing to do because you don't sort of know what your sampling unit should be. In the previous example with the weblogs, and I'm just after the mean, I just take some rows, right? Because there's no dependency among the rows, it doesn't really matter. But in an example like this with the song, maybe I should take entire verses or at least entire lines. But if I just take words, 10% of the words does not give me 10% of the information in the song, right? In fact, I have no idea what this song is about.
Oops, I did it again.
Yeah, you're right, right? But, someone will know, right? Someone will know. So anyway, that's the final word on sampling. Okay, any questions about that? So the point is sampling is not that obvious. You can't just say, oh, I have a lot of data, let me take a sample. Because unless you really know the relationships in the data, you can't really just say, I'm not going to lose anything by taking a sample because you might break some of them. Okay, now that's really all I wanted to say about chapter 2. Chapter 3 is sort of a very interesting chapter, one of my favorites. It's probably my favorite chapter that we'll do because we get to make graphs and things like that. It's called Exploring Data. And they divide the chapter, so 3.2 deals with, you can either explore data numerically using like summary statistics, like the mean, the standard deviations, so the percentiles, or you can do it visually using tables and graphs. And they start off with the summary stats in 3.2, but then they do the visualization in 3.3. I'm going to begin with the visualization, and I'm going to argue to you that that's actually sort of the right order to go in, because you've probably seen people before that they get some data. The first thing they do is compute the mean. Well, if all the data is between, like 0 and 100, and one number is like 1,000,000, then computing the mean probably isn't the right thing to do until you throw out that huge outlier. So you would catch that with visualization, but you might not catch it with summary statistics. So usually the advice is to start with visualization, and that's what we're going to do. I'll also note that as we go through this chapter and talk about visualization, many of the techniques you would use to explore data visually, you would also use to present data. Now, the types of graphs that you're going to use for presenting might be different from the ones you want to look at just when you're exploring, but a lot of the techniques are similar, and things that are meaningful to you as you're exploring the data are also likely to be meaningful to other people as you're presenting the data to them. So page 105, they start talking about visualization. They say visualization is display of information in graphical or tabular format. Successful visualization requires the data be converted into a visual format so the characteristics of the data and the relationships among the data items or attributes can be analyzed or reported. Goal of visualization is interpretation of the visualized information by a person and the formation of a mental model of the information. So usually if you think about in terms of presenting, people may not remember the numbers you gave them or the table you gave them, but they'll often remember the picture that you gave them, right? And they say, the picture is the thing that makes the impression on people, and they'll say, oh, that's that report with that picture. And we make fun of people, they didn't actually read the report, they just looked at the pictures, but the pictures should sort of be the most meaningful thing and the thing where you can sort of say the most. And so that's why we'll spend some time talking about different pictures that you make for data in this chapter. Okay, so this is sort of a really toy example, but I like the fact that it's a toy example because if you can't see what's going on with 40 numbers, imagine that you have 40 million numbers. You really can't see what's going on. And so here I just have 40 numbers. I taught a class once with a 200-point exam, and these were the 40 scores. And so the question is, okay, you're the professor. You get back these exam scores. How'd the class do, right? What do these numbers tell you? Well, if you just look at numbers, you say, well, it just looks like 40 numbers. I mean, you can start to look and you can see, well, at least no one got a 2-digit number, because I would notice that right away, so at least everyone got over 100. But it's really hard to see sort of anything interesting in this data. Now, there's only one attribute, right? It's their exam score. So I'm not looking for relationships. So with only one variable, what I would be curious about is what is the distribution of this data? And the way to look at the distribution of this data is what your book talks about, a histogram. So you've probably seen this before. So one thing you might get out of this if you are familiar with these is how to make one in R. So what is a histogram? Basically, it's a plot, okay, and it displays the distribution of the data by basically dividing the possible values into bins and showing the number that fall into each bin, right? So with those exam scores, you might go 100 to 105, say how many people were there, 105 to 110, so how many people are there. You can also make them relative frequency by simply dividing the counts by the total, which would be useful if you were comparing different size groups. The table that goes with it's called a frequency distribution, and in R, there's a function HIST that's useful, and let me demonstrate that to you. Now, the nice thing about the histogram is it does scale well, right? Because it doesn't matter, here I have 40 numbers, but it doesn't matter if I have, 40,000 numbers, because I get to choose how many bins I'm going to make, and the counts, can get big, and I can just rescale my y-axis. So the histogram is fine for large data sets. It might take you a while to compute, but it's a good way to summarize it. Let's look at this hist function in R. So I said make a frequency histogram in R for the exam scores using bins of width 10 beginning at 120 ending at 200. So we'll go 120, 130, 130, 140, etc. like that. So here's what you do. So first of all, this is just reading in the exam scores, right? There's no header, so I say header equal false. Then I call the hist function. Now, some functions in R for plotting will sort of automatically plot for you, whereas other functions need to be called within the plot function itself. So this is one, if you just call hist, it automatically makes a plot for you. I'm going to plot the first column of the exam scores. There's only one column, so that's going to be that. Then I specify the breaks, and here I'm going to use that seq, the sequence function, 120, 200 by 10. So that's going to be a vector that goes 120, 130, 140, etc. Color, COL is color. You have to quote the color, otherwise we'll look for an object named red. X label, Y label, these are, whenever you're plotting in R, you usually get to specify these or override the defaults. That's the x-axis label, that's the y-axis label. Then the main is simply a title on the top of the plot, and there's usually a default value. So if you don't want a title up there, you could just put quotes with nothing in there. So I'm claiming this is going to make a histogram for you. Let me sort of demonstrate that to you. So exam scores here. Let's see. So you can see we have exam scores now. There's all 40 of them. And what else am I going to do? Call the histogram function. And there you go. There's your histogram. So you can also see, so the labels are the labels I put on there. if you wanted to do, you suppose you said, okay, I want to do 100 to 200, right? You don't want to start at 120. Well, you could do that too, right? You would have just set this to be 100. Suppose you don't like red. Suppose you want it to be pink. X label, I'm going to leave the same. The main, maybe you don't want any title at all. You could change that. And Windows device. There you go. There's a different one starting at now 100 as opposed to 120 and now pink. Okay, so it sort of gives you flexibility to do things like that. The other thing is if you don't want the plot, you just want sort of the counting done for you. I'm going to show you in a second how you can get the histogram function to actually give you values as opposed to making plots. But by default, it's just going to spit out a plot at you. And that's called a histogram. Now, what can I see in this data? Well, I can see things that I didn't see before. I start to see that, like, there's a lot of people here, a lot of people here, but it's curious that there's not that many people there, right? You might sort of expect sort of a unimodal thing, but it almost looks like it could be bimodal. Now, with a sample of size 40, I don't know if this thing is really going to persist, but as an instructor, you might worry, right? If you're grading people and a whole bunch of people are here and a whole bunch of people are here, but there's no one really in the middle, you're trying to tailor your lecture to sort of hit the people in the middle, and what happens is you're not hitting anyone, right? Half the people are saying this is too easy, half the people are saying this is too hard, no one's happy. And you're not just going to see that by looking at a list of numbers, but when you start to look at the distribution, you see it, right? You certainly wouldn't see it by looking at the mean, because you probably see, oh, the mean is right there, and you think things are perfect, right? The mean is like a C or wherever I want it to be. But it looks like it might be a little bit bimodal, which would be of concern, okay? So I think that takes care of the histogram. Any questions about making a histogram in R? The plot window, if you want to sort of save your plot, you have a few options. So one thing is there's commands like PostScript and PNG, which sort of, if you look at PNG, basically you call the PNG function, and then whatever plots you produce after that will be written out to whatever file name you specify. PostScript is analogous. If you're just sort of playing with it in a Windows environment here, and you make a cute plot, and you say, where'd my cute plot go? You say you make a cute plot, and you just want to immediately save it, right? You don't want to have to go back and do anything. Then it actually lets you sort of click and save it, right? So you can click on this thing and do File, Save As, and it lets you export as PNG, PDF, JPEG, anything you want there, PostScript. The PostScript, I think, is encapsulated PostScript, which is usually what you want. So anyway, the plotting in R is really nice. It gives you a lot of flexibility. Later on in this chapter, I'll show you how to sort of change a lot of the other parameters in the plotting. But there is my histogram for my exam scores for that toy data set. Okay, any questions about the histogram in R? Okay, so that's one basic plot you can make. Now, sometimes you don't want to make a histogram with these bars, right? If you look at some of the plots that people make, having the bars is a little bit childish, and you're sort of wasting a lot of ink that it doesn't really need to be there. So what people sometimes do is they just sort of take the midpoints of the histogram and they connect those by lines, and that's generally called a polygon, or sorry, frequency polygon, or it could be relative frequency polygon if you divide by the total to make them decimals. They don't talk about this in the book, but I mean, from a histogram, it's easy to generalize. By convention, we usually, like I said, use the midpoints of the histogram bins, and then they include 2 extra bins at either end, just so you get it going back down to 0 so it looks complete. And I'll demonstrate that for you. Now, there's no function in R that I know of to make a polygon, but that's okay, because you can trick the histogram function into making a polygon for you. And so here I said basically make the polygon in R for the exam scores. Same bin widths, start at 120 and at 200. So this is how I do it, and let me explain to you what's going on here. I first create an object that's called my histogram, and I call it the same as I did before, exam scores column 1, breaks 120 to 200 by 10, but then I say plot equal false. And some function like histogram that by default produces a plot, when you say plot equal false, it's not going to produce a plot anymore. It's going to create this object. Well, let me just sort of show you what's in the object, because a whole bunch of different information is in the object that would be used to plot it if you were plotting it. So when I do this, okay, I get an object that's called my hist. And what does it have in it? Well, it has a bunch of things. It has an attribute, I don't know what that is. It has the midpoints, has the density, which would be if you scaled it to an area of 1, has the intensities, which look like the same thing as the density, has the counts, okay, so that would be useful. And I think it has one other thing that you can't see here, which is the bins. So it has the midpoints, the 125, 135. It also has the 120, 130. So for example, if I say counts, let me grab the counts out there. Counts store as my histogram $counts. It's going to give me the counts that were up here, right? It's going to give me a vector of those numbers. So now the counts I've stolen from the histogram function. I've stolen the counts, and I can also steal the breaks. That's what it calls, the 120, 130, etc. Breaks. So I've stolen the breaks from it. So basically, the histogram is nothing more than a plot of these numbers and these numbers. You know, this on x and this on y. And so is the polygon, right? So once I've stolen those out, I can use R to basically make a plot of these numbers as a function of these numbers, make points, connect them by lines. And so in R, there's this really great function called plot. And this can sort of basically make, you know, plots as you would want to specify them, right? You specify what you want to plot on the x-axis, what you want to plot on the y-axis. Now in this case, I did 115 comma breaks plus 5, right? So the first breaks was 120, 130, et cetera. So this would be 115, 125, 135, 145. So that's what I wanted to do when I said I want to use the midpoints. I don't want to use the 120 and the 130. I want to do that. And then, of course, I put a 0 at either end. So 115 gets a 0 and 205 gets a 0. And you'll see this when I make the picture. PCH, I'll talk more about this next time. But whenever you're plotting in sort of these stat software packages, using the defaults is not always a good idea for a couple reasons. One is they don't often look good, and two, people sort of know that you use the defaults, and they maybe, you know, associate you with someone who doesn't know what you're doing. So, you know, I mean, it's like the same thing in Excel. When you see the gray background, all you think is they don't know how to change that, because clearly it doesn't look good. So the default in R is to make the points with little circles. So I tend to like PCH equal 19, which makes the points as solid dots, which A looks better and B tells people I know what I'm doing. The X label and the Y label, I specified those before, and then the main is the frequency. So let me just sort of show you that. And again, let me stress that the syntax for plot is the vector of X values, comma, the vector of Y values. And of course, those have to be the same length, or it will complain, right? So what do you want to plot on the X, what you want to plot on the Y, and then by default, it's going to make a scatter plot. So let me sort of do that part for you here. And Windows, there we go, right? So the 115, 125, 135, et cetera, was specified there, and then the Y values were the frequencies with the extra 2 points at 0. And so then the only thing else I have to do to make the polygon is to connect these points, because whenever you're making a graph like this that you're trying to read, you know, it's hard to see if you haven't really connected the points in order. So there's another great function in R called lines. And the lines function takes pretty much the same arguments as plot. You can't specify these many things again, because the line function actually is just going to add to the plot. And so I give it the same x values as I did plot, and I give it the same y values as I gave plot. And it basically goes back into plot and connects the plot points with lines. So plot and lines together, you know, plot's going to give me a plot with points on it, but then lines, if I give it the same x and same y, will connect those points with lines. And so let me show you that here. And again, it's not going to overwrite the plot. It's just going to sort of sit on top of the plot. And there you see. And R is kind of like the last thing you add is the thing that's on top. Now, nothing's being covered up here, but that's the general behavior. So there you see the polygon. This is the same information that the histogram has, but I haven't had to sort of waste ink with the different bars. And the advantage to this is that I could put a second one on the same plot, and nothing would cover anything up, because you can imagine you could not put two histograms on the same plot, right? You can't put two bars. The bars would cover each other up. And let me just sort of show you that, in fact, this is the same as the histogram by doing the following. PAR, actually, maybe I'll write that down now, is sort of the answer to all your plotting questions. And we'll talk more about that next time. But it sort of lets you control everything. And in this case, well, I'll just show you, PAR, right? You can just read this, and after you read it, you'll make the following generalization. I can do anything I want when I'm plotting in R, and there's probably some three-letter string that specifies it, right? So lab, las, all these little things do a lot, and you can just keep reading. In particular, this time I am after the function called mfrow. Oops, mfrow, which specifies how many rows and how many columns I want. So I want to try and put two things on the same plot. So I'm going to do, actually let me do 2 rows and 1 column. Okay, so oops. So now, whoa, so I think I need an equals, not a parenthesis. There we go. So now everything I plot after this is going to sort of, 2 things per plot, right? So if I go back, well, let me plot this one that I just plotted, the polygon. Paste this, and then paste this. I'll talk more about the power function next time because it does give you a lot of flexibility. And if you look at the plot now, it's the same plot before, but it sort of squeezed it onto half of the page, right? So same polygon as before, sort of squeezing onto half of the page. Now that I do that, I think I maybe actually like it better the other way. Oh, I'll leave it. Okay, and then if you go back and compare it to the histogram you made before, you can see how the polygon relates. It's the same picture. Oops. What happened? I closed it. Okay, well now's my chance to fix it. Okay, so let me do 1, 2. Okay, and then the histogram. So histogram. Okay, there's the histogram. Now don't close it and make the polygon. Where's the polygon? Here. Okay, where are the lines? Add the lines. There they are. Okay, so now is the picture I was after. There you go. You get to compare the 2 side by side. So you see that's really the same information, that I simply put a point here, a point here, a point here, right? Point here, point here, point here. Then there's just have these 2 extra guys, right? So that when you come here, you don't want to leave them hanging in the air. You just sort of go down here. So this point is at 195, right? 190, 200, 195. Then this would be 200, 210. So the last point, just for equal spacing, goes at 205. So that's called a polygon. It displays the same information as a histogram, but I haven't sort of wasted ink. I still see that my class scores are sort of bimodal with a lot of people here, a lot of people here, but not many people in the middle. And the nice thing is if I gave a second exam, I could make the polygon on the same plot and I could compare them, whereas it would be impossible to make 2 histograms on the same plot because the bars would cover each other up. Okay, so that's the polygon, and I think that's all I wanted to say about that. Any questions about the polygon in R? Question?
This is just about the visualization in general.
Mm-hmm.
If your exam only went up to, say, 200, would it make sense still to have that extra 0 hanging off above 200?
Yeah, I think it's not so bad. It's just you probably wouldn't want to put 210 there. Like, I think you like to keep the equal spacing, but it's really, if it ended at 0, you wouldn't want to put like -10. I think it's okay, because you like to keep the equal spacing, but like, you probably don't want to label it because it would look stupid. Yeah, that's a good point. So if it really stops at 200, his question is, why does the graph go beyond 200? Okay, any other questions about the polygon or the histogram in R? Okay, so both of these show the distribution of scores, and so within any bin I can see sort of what's the count or what's the percent. Sometimes though, what's even more useful, and I'll probably try and give you some examples of when it's more useful, is to look at the, so there's my answer on the slide, is to look at the cumulative distribution, right? So not what percent got in this bin, but what's the total percent less than each value. And of course we call that the cumulative distribution function, right? Cumulative means, accumulate, right? The percent less than each value. And so in statistics, you'll hear sometimes people talk about the CDF, which is the cumulative distribution function, right? It starts at 0, ends at 1 or 100%. And this is, for any point, is basically the probability of being less than that value. So what we have when we have data is we have the empirical cumulative distribution function, right? So for any point, I know the fraction of points that are less than that value, right? So what percent of exam scores are less than 100? What percent are less than 120? What percent are less than 200, right? For any value, this function returns the percent that are less than that value. And sometimes people call the plot of this thing, the plot of the empirical cumulative distribution function, sometimes they call it an ogive, which, I don't know, it doesn't get used that much, but just so you know. It's not in the book. I thought I mentioned it. Anyway, someone wrote, right, R is open source, so someone wrote a nice function called engEDU in R that does a pretty good job, as far as I can tell, of plotting the empirical cumulative distribution function. And of course, you can think about how do you make that thing, right? You simply say, okay, this would be like the exam score, and then this would be, the cumulative percent. And it would start off, at 100 or the lowest score is at 0, and it would work its way up to 100% right here. And it would simply go up by 1 over n every time someone scored, or if 2 people got that score, it would go up by 2 over n, right? So some sort of plot like this, and then how would you use it? Well, I'll show you. I mean, you can say, okay, here's 50%, so what's the median? Right there. Okay, what percent got less than this value? Well, that percent did. And so sort of show you how this thing works. So this thing says, make a plot of the empirical cumulative distribution function for the exam scores using the engEDU function in R. So how do you do that? Well, I told you that the R is kind of funny, right? That this function, engEDU, does not, it's much different from histogram, right? It doesn't by default produce a plot. It actually is written so that you're supposed to call plot and then inside plot put this thing. And that's not consistent at all with the behavior for histogram, right? Histogram, when I called histogram, I got a plot. And if I wanted sort of values out, I had to sort of say plot equals false. With this function, by default, I get values. And if I want to plot it, I have to put it inside plot, which is sort of curious. So, you know, if you sit at home and you keep typing engEDU and you never see a picture, it's because I have to say plot of that. OK, so engEDU of the exam scores, column 1, which there's only one column. But if I don't say column 1, it gives me an error. Verticals equals true. Why? Because verticals defaults to false, which means that it only has horizontal lines, never has vertical lines, and it looks really ugly. Do.p. Okay, do I want it to plot the points? That's what that means. No, I don't, right? That's as far as I can tell. Because by default, it puts these little points on there as circles, and believe me, it looks better without it. Maybe I'll do one by the default, and you can see the default looks pretty ugly. The main, I just put a title on the top. X label, Y label, you know, you can always specify those. The nice thing, though, when you make a plot, you know, this is sort of one of these elementary things, but label the axes so that the person doesn't have to read anything to know what the plot is saying, right? So if you've labeled the x-axis exam score and the y-axis cumulative percent, then everyone's going to know what that plot is plotting. If you don't put labels there, then you know someone's going to pass around your plot and no one's going to know what it means. So I always like to put labels on the plot that are sort of enough for someone to know what the heck it's saying. Okay, so this is going to work to make empirical cumulative distribution function. And so I say here, and there we go, okay? And you can see what's going on here, right? So, you know, no one got below here, and then someone got a score there, right? So it goes up by 1 over n. And then someone got a score here, so it goes up by, you know, another 1 over n, et cetera. And like, it looks like 2 people scored here, so it goes up by 2 over n, et cetera, et cetera, et cetera. And in the end of the day, you know, the highest score was somewhere here, and so then it goes, you know, at 100%. How is this useful? Well, I want to know what percent got less than 160. So I go here, and it looks like about 30%. I want to know what the median is. So I look at 50%, follow it over here. Median looks like it's 170. You know, I want to know what the 90th percentile is. Follow 90 over here. It's like there. OK, so it's very nice like that. And you imagine as you get more and more data, it's only going to smooth out more and more. So that is your plot of the empirical cumulative distribution function. While I'm mentioning it, I'll just say to you that if you don't, if you don't change the defaults, you can see that it sort of is ugly. So if I just say this, right, I'll get a plot, but it won't look that nice, I think. Let's see, where's my plot? There you go. By default, it doesn't have the vertical lines in there, and it has sort of like these circles. So I don't know, I just sort of thought this thing was ugly, so that's why I showed you how to change those defaults. You also see that it just labels this as X, you know, and then this is sort of meaningful if you're, well, I don't, maybe not. F of X is usually the CDF and stats, and then, you know, this is completely unmeaningful. So that's why I like to change those. I'll show you too, like, you know, that, again, it is open source. So if you look at some function like this, you can see here, like, the documentation isn't that good, but the nice thing is he provided a whole bunch of examples. So you can always just sort of paste these in and see what they do and change the values and see what's going on. You know, so it's examples instead of documentation. Or you just email the poor guy and you tell him, you know, I have no idea what your code is doing, you know. And so anyway, it is open source, so it's good to sort of, and a lot of times authors, when they write books too, will actually write their own libraries. These authors did not, because it's not really an R book, but a lot of times they will write their own libraries, and you can sort of play along with the book and the R at the same time. So there's the one I put up on there. The last thing, well, I think I'll just save this, right? But the next thing we're going to talk about is, if you have another set of data, right? So here at the end of the semester, I give a second exam, and I want to compare these scores to the other scores. How can I do this? Well, with the CDF, the eCDF function, empirical cumulative distribution function, no problem putting those on the same plot. Same thing with the relative frequency polygon, right? You could put those on the same plot. It doesn't matter that there's fewer scores here. It looks like 3 people dropped out of the class. It doesn't matter, right? One has a denominator of 40, the other has a denominator of 37. As long as you're working with percents as opposed to counts, it won't be any problem. So next time I'll go through and show you how to put sort of 2 polygons on the same plot, 2 empirical cumulative distribution functions on the same plot, and we'll talk about sort of general other types of plots you can make in R, and I'll make a plot of the web logs, and you can see some spikes that are curious. So the next lecture we'll do a lot more with plotting, and I think that's all I wanted to say today. Any questions before we take off? Question in the back.
Way to actually make it give percent on the left side and not
Yeah,
fraction?
you can basically, well, to tell eCDF to give a percent, you probably have to go back, output take the output from that function, divide it, and then plot it again, unless he has put something in there to do it, but he may not have. So you don't want it to go from 0 to 1, you want it to go from 0 to 100, right? If you didn't put an option there for you to do that, what you do, instead of plotting it, you create an object, or you get the output from it, you take that output, divide it by 100, or multiply it by 100, and then put it back in there. So. Other questions before we take off? Okay, I'll see you guys Tuesday.